Hello, the purpose of this mini lesson is to discuss the basic characteristics of the exponential function, the basic exponential function. So if we have an equation of the form like this, f of n equals 2 to the exponent n, this is an example of an exponential function. The general form for the basic exponential function is this: f of x equals a to the exponent of x, with a greater than 0, meaning positive, and a not equal to 1. Why is it that we have these two restrictions? A cannot be negative because if we were to have a negative number as a base, you can see that as the exponent changes, the value of the outcome would change from positive to negative. So if we have, for example, negative 2 as a base, negative 2 to the exponent 0 is 1. Negative 2 to the exponent 1 is negative 2. And then negative 2 squared would be positive 4. So we would be having a positive value, then negative value, etc. And that doesn't render a function. So that is why a has to be greater than 0. Why can a not be equal to 1? Well, you can imagine that if we had 1 to the exponent of 0 is 1, 1 square is 2, is 1, excuse me, 1 cube is 1, and so on and so forth. So the function will always be equals to 1, which is really not an exponential function, it's more like a linear function. A, this parameter a, is known as the constant ratio, and this is the factor by which the function grows or decreases as the independent variable changes. In our example, a equals 2. F of n, 2 to the n, a means 2. That means the function doubles each time. We're going to explore these in a little bit more detail next. So here is our basic function, an example, f of x equal 2 to the exponent of x. And this is what the graph will look like. You notice it's a curve, is not a linear function, is not a quadratic function. And we can see it has, it's increasing. The y-intercept is at 0, 1 because when x is 0, 2 to the exponent 0 equals 1. And the function keeps getting bigger. One other key characteristic is that this function is asymptotic to the x-axis. What does that mean? That means as the value of x gets very, very small, let's say we put a very large negative number as our exponent, our output be very, very small. We get close to 0, but it will never be 0. So the asymptote to this function is y equals 0, or the x-axis. That means the domain can be any real number for this function. X can take any value, but the range is restricted. The range can only be values greater than 0, any real number greater than 0. Now let's take a look at what a table of values would look like. So here we have values for x from negative 2 to 4, and we can see what happens when we take x and raise it to the exponent, we take 2 to the exponent of x. So for example, at 0, we have 2 exponent 0, which is 1. And at 1, we have 2 exponent 1, which is 2, and so on and so forth. If we have negative exponents, 2 to the exponent negative 1 is the same as 1/2, which is 0.5. And 2 to the exponent negative 2 is the same as 1 over 2 squared, or 1/4, which is 0.25. So just by looking at the equation, we can ascertain that the constant ratio is 2, and that means each value is twice the previous one, as we can see here on the table of values. So by just looking at the equation of this basic function, we can tell that it's doubling each time, and the table of values will be that. Now, what happens when we change that value of a? So let's say we have a equals to 3. So what would happen to the y-intercept? What would happen to the asymptote at the x-axis? What would happen to the constant ratio? What would happen to the graph? and the table of values. So if you want to pause and think about these for a moment, please do so. And then we're going to reveal what the answers for these questions. Well, so when a becomes 3, the y-intercept is unchanged, because that means the y-intercept we know happens when x is 0. So that means that our y-intercept would be at 3 to the power of 0, which is 1. So that means the y-intercept is unchanged. Similarly, the function would still be asymptotic to the x-axis. No matter what values we put for the exponent, it will never be 0. The constant ratio does change. Now the constant ratio is 3. So the values, instead of doubling each time, they would triple. So that is an important change. And we're going to see in the next slide what happens to the graph, and the slide after that, what happens to the table of value when a is 3. So here it is. Our equation would be now 3 f of x equals 3 to the power of x. And this is what the graph looks like. Notice that the blue line is the graph of 2 to the exponent of x. So it was left there for us as a reference. Notice the y-intercept is still unchanged. And as x is positive, 3 to the power of x grows faster than 2 to the exponent x because the numbers are tripling. However, when x is negative, then this function grows at a slower pace than f of x equals 2 to the power of x. And then when we look at the table of values, this is what we have. So let's take a look at some of these values that could be a bit tricky. So when x is negative 2, that means our function is 3 to the exponent of negative 2, which is the same as 1/3 squared. And 1/3 squared is 1/9. When x is negative 1, we have 3 to the exponent negative 1, which is 1/3, and 3 exponent 0 is 1, and these are friendly enough for you to see that what they are. And our common ratio now is 3, so our values triple each time. Okay, so now let's look at another variation of this. What happens when a is 1/2? In other words, a value between 0 and 1. And the same questions, what happens to each of these elements? The y-intercept, the asymptote, the constant ratio, and the graph, along with the table of values. So again, take a moment to think what would happen if a was equals 1/2. In other words, our function would be f of x equals 1/2 to the power of x. Well, the y-intercept would be unchanged, because we would have at x equals 0, which is where the y-intercept occurs, 1/2 to the exponent 0, which is equals to 1. So that is unchanged. And similarly, the asymptote would still be the same. In this case, no matter what large number we would put for the exponent, it would never be 0. So this function is also asymptotic to the x-axis. The constant ratio is now 1/2. So this time the values would halve each time. And we're going to explore what happens to the graph and the table of values in the next 2 slides. So here's the graph. Again, the blue line shows us f of x equals 2 to the exponent x. In this case, we have f of x equals 1/2 to the power of x in black. Notice that the y-intercept is the same. The graph is still asymptotic to the x-axis, so that didn't change. However, this is a decreasing function over the domain. We can think it is a reflection of f of x equals 2 to the power of x over the y-axis. So this function is decreasing. And that makes sense because each time the values are half of the previous ones. So this function is a decreasing function. Let's look at the table of values. Now, if we were to evaluate some of these values for our function f of x equals 1/2 to the power of x, we would have, say, when x is -2, we would have 1/2 to the exponent -2. And that is equivalent to 2 squared. 2 squared is 4, and so on and so forth. When x is -1, -1/2 exponent -1 happens to be 2 to the exponent 1, which is 2, and we already talked about the y-intercept, and you can see this time the values are half of the previous one as the function, as the x changes. So in summary, the basic exponential function has this form. F of x equals a to the exponent of x, with a not equal to 1 and a greater than 0, only positive values. A is the common ratio, is the factor by which the function grows or decreases. If a is greater than 1, then we have exponential growth, a graph that looks like this. If a is between 0 and 1, then we have exponential decrease or decay, as shown in this graph. The y-intercept is always 0, 1, regardless of the value of a, and the graph is always asymptotic to the x-axis. So these are the key characteristics of the basic exponential function, f of x equals a to the power of x. Thanks for watching.